In this video, we're going to introduce some simple patterns of chemical reactivity. So by that, we mean if we're talking about the pattern that we see, we can define it as what's called a combination reaction when we have two or more substances that react and they form one product. So that's the pattern for a combination reaction, this first type of reaction here. So, and we see that in these examples shown below. We have 2 moles of magnesium, 1 mole of oxygen, and we end up with 2 moles of those combined in magnesium oxide. We see in the second example, 2 reactants, so nitrogen gas and 3 moles of hydrogen gas combined to form one product, our ammonia gas on the product side. And then we see, lastly, this C3H6 gas combines with bromine, and we end up with one product. So we can see solid and gas combine to form solid, gas and gas combine to form gas, or gas and liquid to combine and form liquid. So any combination of phase of product and reactant, that won't be one way to differentiate a combination reaction, as we can see, due to all different phases being represented here. And just so you know what's going on in these images here, this is some magnesium ribbon. It's usually you can add a flame or a heat source to start a reaction with atmospheric oxygen. And then we see this bright shining magnesium ribbon when it's being exposed to oxygen here in the middle. And then this is what happens afterwards. This is the magnesium oxide product over here, the solid. So let's take a look at the next pattern of reactivity, of reactions that we might see, something called a decomposition reaction now. And this is kind of the opposite of the combination reaction indicated above, where now we have one substance that decomposes or breaks down into two or more. So you might have 2 products, you might have 3 different products, etc., depending on the reaction. So we see solid calcium carbonate. It can be heated or decomposed in some other fashion, and we get solid calcium oxide and then also CO2 gas. So one thing turns into 2 or more. That's the pattern for a decomposition reaction. Then we have potassium chlorate here, which when that decomposes, we get 2 potassium chlorides and some oxygen gas. And then lastly, we see sodium azide here. We get some sodium metal and then nitrogen gas. So let's see if we can take our skills from our discussion of nomenclature and phase indication for reactants and products, see if we can write the balanced equation for the combination reaction. So that's what we're going to be looking for, our pattern of lithium metal. So that's telling us the phase will be solid, and then fluorine gas. So let's write down what we know so far. So we have lithium metal, that's going to be solid. And for metals, we just write a single elemental symbol. So this is lithium, and this may or may not be balanced. We may only need one. We'll find out when it combines with fluorine gas. And fluorine was one of those diatomic molecules that always has a 2 subscript. So let's review. We have this acronym, or this kind of memory device where we could say horses need oats for clear brown eyes. And this reminds us that all of these are the diatomic, Cl2, sorry, after the L, bromine, iodine. So fluorine would be included in this group of diatomic molecules. So we would indicate it like so, and then we'll put a G for gas phase. So we yield what's called lithium fluoride here, and we can create this compound from the predicted charge. Lithium's in group 1. It will become a +1 ion. Fluoride's in group 7. It shall become a -1 ion. We crisscross our charges, and then we see that our product will just be Li and F, a 1-to-1 ratio of lithium and fluorine. So when we create this ionic compound over here, you may not know this, but they are generally going to be solids because they have fairly high molar masses and things for that reason. But we see that we have an unbalanced reaction now. So we have one last step here where we need to set equal the number of lithium and fluorine on each side. So let me give us some more room here. And then we have lithium and fluorine on the other side. And we only have one of those. So we have 1 and 1, and here I have 1 and 2. So I know that I'm going to need a 2 over here. So that will change both my lithium and my fluorine. And then over here on this side, I just need to change my lithium. So I added 2 coefficient. So this would be our final answer, if I could get every phase in there. We have 2 moles of lithium solid combined with 1 mole of fluorine gas to give us 2 moles of lithium fluoride. So that's how you could complete a question like that. And let's look at one other example here that now shows a decomposition reaction. So we're told that we have solid, so the phase is given, barium carbonate. So if we remember, barium's in group 2, carbonate is a -2 ion, polyatomic ion. So when they combine, it's 2 to 2, which reduces to 1-to-1 ratio. So this is our molecular formula, or chemical formula for barium carbonate, and it's solid. So we're told that it is heated. So sometimes heat is indicated by drawing a little triangle over our arrow here. So we're moving in the forward direction. By adding heat, we get 2 products. So we get barium oxide. So now I know Ba is a +2. We'll keep that up top just to remind us. Oxygen as oxide is a -2. So when they crisscross, we get that 1-to-1 ratio again, as we did with the barium carbonate. So this is the correct formula for that solid, barium oxide. And then we have our other product, which is carbon dioxide. This is a molecular compound. So we have 1 carbon because there's no prefix, and we know mono is not used. And then oxide, dioxide indicates 2. And this is generally a gas under normal temperature and pressure. So let's take a look. Do we need to balance this reaction? Well, we have our barium, and then we can keep our carbonate together if it remained carbonate on the other side, but since it did not, I do have to separate my carbon and oxygen, and I can easily do that over here. So I have one of those, 1 carbon, 3 oxygens, 1 barium, 1 carbon, and 3 oxygen. So even though the carbonate broke apart into the oxide portion and the CO2 gas, we still have a balanced reaction right from the very beginning.